Good morning, students. I am Sweta Agrawal, working as Assistant Professor in Department of Chemistry, Janta Vedic College, Barod, UP. Today we will learn an interesting topic, kinetic theory of gas, means molecule of gases in motion. So, in this session, we will try to understand theoretical model through postulates of kinetic theory of gases. Then we will see various laws studying the behavior of gases. Then Maxwell distribution of molecular velocities. Then what is the difference between the real gas and ideal gas, and the deviation of the gases from ideal behavior and their explanation through Vander Waals equation. So, we all hear about states of matter from our school days. Basically, there are three states of matter: solid, liquid, and gas. But in this newly explored era, we have two more, that is Bose Einstein condensate and the plasma. And the gaseous states are the simplest states of matter, which we will study here. So, individual molecule of gas possess physical property of mass, momentum, and energy. So, in order to study the behavior of gas, we must use a theoretical model that is known as kinetic theory of gas. So, before going into this, we have to read some postulates. See, this is a closed container in which there are so many gaseous molecules, and these gaseous molecules are moving in a random direction in all the possible directions. When we consider the volume of a single gas molecule, it is considered as negligible in comparison to total volume of gas in this container. Now, while doing movement, this molecule undergo collision with one another and further undergo collision with the walls of the container. So, from this picture, you can state that postulates. First is gas is comprised of large number of teeny constituents known as gas molecule, and its volume is negligible in comparison to total volume of gas. Second is these molecules are in the state of constant rapid motion in all the directions, colliding with each other and with walls of container. And third one is the molecular collision is elastic in nature, means whenever they collide there is no loss of energy, right? Fourth point says that the laws of classical mechanics and Newtonian mechanics are applicable. And the fifth postulate is there is no force of interaction between them. These postulates study the behavior of gases. Further studying the behavior, we have so many laws. First is Boyle's law. Boyle states that pressure is inversely proportional to volume, means when we are decreasing the pressure, volume is increasing, or V1 is equal to V2 V2 at a constant temperature. Second is Charles' law, which states that volume varies directly as the absolute temperature at constant pressure, means V1 by T1 is equal to V2 by T2. And the third law is Avogadro law, which states that at constant temperature and pressure, equal volume of gases contain equal number of moles. That is V1 by N1 is equal to V2 by N2. Combining all these three laws, Boyle's law, Charles' law, and Avogadro laws, we get an ideal gas equation, that is PV is equal to nRT, where P is pressure, V is volume, N is number of moles, R is gas constant, and T is temperature. Now, understand the Maxwell distribution of molecular velocity. See, all these molecules are in random motion, so they possess some velocity. So, Maxwell, along with Boltzmann and other scientists, plotted the fraction of molecules on y axis along with their velocity on z axis. What they discovered is the molecules having the very high or the very low velocity or the very high velocity, they are very small in number, and the area which they plotted under the curve. This distribution curve area shows the total number of molecules. And the third most interesting point is the velocity which is possessed by maximum number of molecules, which is known as the most probable velocity, and it represents the peak of any curve, this one or this one. And see, they have plotted the velocity distribution curve under three different temperature. We know when we increase the temperature, obviously molecular velocity goes on increasing. So where the velocity is very high, this curve, so the temperature of this curve will be high. That is T3 will be greater than T2 and T2 will be greater than T1. So how many types of molecular velocities are? Basically, there are three types of molecular velocity. First is average velocity, which is expressed by under root 8 RT by pi m. Second is root mean square velocity, which is expressed by under root 3 RT by m. And the third is most probable velocity, which is expressed by under root 2 RT by m. So, now understand what is ideal gas and what is real gas, and then we will see the deviation. So, what are ideal gases? We have already seen the ideal gas equation. The gases which follow the ideal gas equation are known as ideal gases under all conditions of temperature and pressure. But do anything is ideal in this universe? No. So same with the gases. We have real gases. So what are real gases? Real gases are the gases which do not follow the ideal gas equation, but they can follow ideal gas equation under some restricted conditions. So what are these conditions? They are having the low pressure and high temperature. Whenever the pressure is low and the temperature is high, real gases will follow the ideal behavior. But when the pressure is very high and the temperature is very low, then the real gases show deviation. So, how do we measure this deviation? This measurement of deviation is best represented by the compressibility factor denoted by Z, which is the ratio of PV real and PV ideal. This compressibility factor determines the types of gases. If the Z value is equal to 1, the gas is said to be ideal. But if Z value approaches less than 1 and the greater than 1, then the gas will be real. Now, understanding the effect of this compressibility factor with two main components, that is temperature and pressure. First, we will see with pressure. See, on the y-axis we have compressibility factor and on z-axis we have pressure. And we have so many gases: carbon monoxide, methane, ammonia, hydrogen and helium. See, this dotted line shows Z value is equal to 1, means which behavior? Ideal. Gas showing ideal behavior. And above this dotted line, Z is greater than 1, and below this dotted line, Z is less than 1. See, when the pressure is very very low, around 0 to 1 atmospheric pressure, the Z value approaches almost 1, means they are showing ideal behavior. But as the pressure is increasing from 0 to 200 atmospheric, the gases show deviation, means Z value is less than 1, means gases are less compressible and there here attractive force is dominant. But as the temperature is increasing more and more at a very high pressure, the lines are above the dotted line, means Z value is greater than 1. This means here repulsive forces are dominant and gases are less compressible. Here attractive forces is dominant below dotted line, and above dotted line repulsive forces are dominant. So Z value is greater than 1. But you can see for hydrogen and helium, there is nothing like Z less than 1. Z is always greater than 1 at any pressure from 0 to 800 atmosphere. Why is it so? Because we are plotting this graph at 0 degree centigrade temperature. And for hydrogen and helium, we need to go to very low temperature, that is minus 48 degree centigrade and minus 242 degree centigrade, for getting this same plot. Now, understanding the effect of this compressibility factor with temperature. See, they have plotted for a N2 gas at different temperature from a very low to very high pressure. What they are getting is at very low temperature, minus 70 degree centigrade, Z value almost 1, and then curve starts decreasing, attaining a minima, and then further starts increasing. And as we the temperature is raised like minus 70 to minus 25 to 20 to 50 degrees centigrade, the dip in the curve becomes smaller and smaller, and at almost 50 degrees centigrade the curve remains horizontal. And when we see in the range of 0 to 100 atmosphere pressure, z value almost approaches 1. This means PV remains constant in this range. And when PV remains constant, which law is it? Yes, Boyle's law. Thus, the temperature at which this Boyle's law occur, which is known as the Boyle temperature. And this Boyle temperature is characteristics of each gas. It is different for the different gases. For N2 gas, it is 50 degrees centigrade. Okay, now why these deviations are happening? There is something happening. So all this kinetic theory starts from air. Where? Postulates, right? So what we have read? First postulates, volume of gas is negligibly small, right? And another is force of attraction is negligible. These two postulates did not hold good for the real gases. So why is it so? When the pressure is very high and the temperature is very low, then we are seeing deviation. So what happened is, see, these are the gaseous molecules. When we apply very high pressure, these gaseous molecules comes very close to each other. They are coming close in such a way that a single gas molecule volume can't be ignored compared to total gas molecule, which remains the same in both cases. And the other postulates which says that there is no force of interaction, which also can't be ignored when the pressure is very high and the temperature is very low. So we will have to correct this ideal gas equation. So another scientist comes, Vander Waals, which says that we need to correct two terms. First one is the volume correction term, and the second one is force of attraction term. That is the pressure correction terms. And get his another equation of state known as Vander Waals equation of state. So what he did, we know ideal gas equation is PV is equal to nRT. He introduced pressure correction term, that is An square by V square, and he introduced volume correction term, that is Nb, and got a final equation P plus An square by V square V minus Nb is equal to nRT, where P is pressure, A and B are the constant known as Van der Waals constant, which is the characteristics of each gas. A depends upon the force of cohesion, B depends upon the effective volume. N are the number of moles, V is the volume, R is the gas constant, and T is the temperature. So from this Van der Waals equation, we get an idea about the deviation of gases from the ideal behavior. Further, in the next session, we will discuss more about the PV isotherm curve using the Van der Waals equation and the continuity of the states, law of corresponding states, and reduced equation of states. Thank you. Any doubts you can ask.